Hi all, today we are going to discuss about the Poisson's and Laplace's equations. So to determine the electric field intensity E, previously we use either the Coulomb's law or the Gauss law when the charge distribution is known or potential is known throughout the region, because by using the formula E is equal to gradient of E. But in some practical cases, only the electrostatic conditions at some boundary conditions will be known, and it is desired to find both the electric field intensity and the potential throughout the region, like example in the case of a capacitors. So in that case we prefer to go for the Poisson's or the Laplace's equations or method of the images. These are three different methods which are used and are referred to as the boundary value problems. Let us see how these things comes. So we know from Gauss law, we know the divergence of D is equal to rho V. So here before proceeding I want to tell you I am writing on a glass screen, so the handwriting doesn't come properly. So I am providing the complete material in the description below. So please go to the video description, there the Google Drive link is there. You can download the complete handwritten material from there. Here you try to understand what I am telling. So from the definition of D, we can tell D is equal to epsilon E. And from the relationship of gradient, we know the gradient relationship E is equal to negative gradient of V. So combining these things, we know the divergence of D I can write as divergence of D is nothing but epsilon E. So this will become minus of divergence of epsilon into gradient of V. So this I am taking as rho V, because divergence of D is equal to rho V, because everything I have substituted, because E I replaced with the gradient of V. So for homogeneous medium, or medium in which the value of epsilon is constant, so in that medium we can tell this divergence of gradient of V, because that epsilon can be taken out. So this will become minus rho V divided by epsilon. It can be taken out, otherwise epsilon cannot be taken out. So this divergence of gradient of V or divergence of gradient of a scalar, this is given by the del square V, which is the divergence of gradient of a scalar. This will be equal to minus rho V by epsilon. So this equation is called as Poisson's equation. Poisson's equation for the uniform medium. So we know this divergence of A we can calculate by dou by dou x in rectangular coordinates with Ax, then dou Ay by dou y plus dou Az by dou z. There is a divergence of a vector. Similarly, the gradient of a scalar, we know this will be equal to dou by dou x of this scalar in the direction of Ax. Similarly, dou by dou y of this scalar in the direction of Ay. Similarly, dou by dou z of this scalar quantity in the direction of Az. This is the gradient how to calculate. So if you want to calculate divergence of gradient of V, so this will be equal to dou by dou x of dou V by dou x plus dou by dou y of dou V by dou y plus dou by dou z of dou V by dou z. So this will be equal to dou square V by dou x square plus dou square V by dou y square plus dou square V by dou z square. It will come as a scalar quantity. In this way we can calculate it. So if the value of rho V is equal to 0, if you are taking rho V is equal to 0 or volume charge density is equal to 0, then this del square V, the Poisson's equations, so that equation will be converted as del square of V is equal to 0. So this del square V is also called as Laplacian of V. So this equation is called as Laplace's equation. That means Laplace's equation is nothing but the Poisson's equations where the value of volume charge density is equal to 0. So similar way I can calculate del square of V for other coordinates. This will be equal to 1 by rho into dou by dou rho of rho into dou V by dou rho plus 1 by rho square into dou square V by dou phi square plus dou square V by dou z square. This is in cylindrical coordinate system. Similarly, this can be written as 1 by r square into dou by dou r into r square dou V by dou r plus 1 by r square sin theta into dou by dou theta of sin theta into dou V by dou theta plus 1 by r square sine square theta into dou square v by dou phi square. This is in the spherical coordinate system. So in this way you have to calculate. So let us take one example so that the how to apply this Poisson's or the Laplace's equations will be clear to you. So it is asked that find potential V at point 2, 1, 3 for the field of two coaxial conducting cylinders. It is given V is equal to 50 volts at the value of rho is given as 2 meters and V is equal to 20 volts at rho is equal to 3 meters. So they are cylinders. So now how to solve this one? So we can apply this del square of V is equal to, because only in the radial directions it is there, because only radially it will be there. So I can write that del square of V will be 1 by rho into dou by dou rho of rho into dou V by dou rho. So remaining components will be equal to 0. So that's why we are not considering, because the potential is varying only with respect to the rho. So remaining dou V by dou phi, dou V by dou z will be automatically equal to 0. So I am just representing here dou V by dou phi and dou V by dou z will be equal to 0, because potential is only varying with respect to the rho. It is mentioned there. Rho is the variable. So this I can write as dou by dou rho of this rho into dou V by dou rho. This will be equal to 0, because this gives rise to this one, or integrating on both sides. So this I can write as rho into dou V by dou rho will be equal to some constant A if you are doing the integration. Then from this I can write my value of dou V is equal to A into dou rho by rho, or again if you do the integration this will become V is equal to A into ln of rho plus B. Let us take it as equation number 1. So let us substitute the boundary conditions. So boundary conditions, it is given there V is equal to 50 at rho is equal to 2 meters. So and second one is V is equal to 20 at rho is equal to 3 meters. I am just substituting those boundary conditions. First boundary condition 50 is equal to A into ln of, it is at rho is equal to 2 plus B. So let us take it as equation number 2. And the second boundary condition 20 is equal to A into ln of 3 plus B. This is equation number 3. So now solving equation number 2 and equation number 3. So we will get the value of A is equal to minus 73.989 and the value of B will be equal to 101.285. So from this I can calculate potential V is equal to 73.989 ln of rho plus 101.285. So it is asked to find the potential at some particular point, potential at 2, 1, 3. So at the point 2, 1, 3, so we can calculate the value of the rho, because here rho is there. Rho will be equal to radius square root of x square plus y square. So x component is 2 and y component is 1. So this will be 2.236. So substituting this in the potential, we will get it as 73.989 ln of 2.236 plus 101.289. This will be equal to 41.745 volts. So in this way you have to calculate. So let us take one more numerical to explain this clearly. I am taking example number 2. It is given that find the capacitance of coaxial cylindrical capacitor where V is equal to V naught at rho is equal to A and V is equal to 0 at rho is equal to B and B is greater than A. This is what is given. So how to find this? Again boundary conditions are given. So here you can see that V is, they are mentioning that it is varying along the rho only. So since V varies in rho direction only, so we can tell that del square of V is equal to 0, or we can tell that 1 by rho into dou by dou rho of rho into dou V by dou rho, this will be equal to 0, or we can tell that rho into dou V by dou rho, this I can take as A because doing the integration. So similar way I can write that dou V is equal to A into dou rho divided by rho rho. I have just rearranged the terms. So from this I am doing the integration, so I can find V is equal to A into ln of rho plus B. So let us apply the boundary conditions. So by applying the boundary conditions, so two boundary conditions are there. One is V is equal to V naught at rho is equal to A, and V is equal to 0 at rho is equal to B. So you will get the values of A and B, and you calculate the value of A and B, and if you substitute, I am directly writing the answer. This will become V naught into ln of B by rho divided by ln of B by A. This is what we get. So from this I can find the electric field is equal to negative gradient of V. So this negative gradient of V will be equal to V naught divided by rho into 1 by ln of B by A. This will be in the direction of A rho. So we know the value of dn at rho is equal to A. This will be equal to epsilon into E at that particular point. So this will be epsilon multiplied by E is this value. So this will be V naught by this rho becomes A ln of B by A. So from this I can calculate my value of the charge Q. The value of Q will be equal to the D multiplied by the area. So this will be epsilon into V naught divided by A times of ln of B by A multiplied by the area at that point will be 2 pi into A multiplied by the length. Or from this I can calculate my value of C is equal to Q divided by V. So substituting the value of the Q divided by V, so I can calculate this value as 2 pi epsilon into L divided by A into ln of B by A. So A is also common, right? So A also will cancel because A will cancel here. So if you are dividing with V naught, Q by V naught, so this will be the value 2 pi epsilon L divided by ln of B by A, because here the potential difference between two plates is equal to V naught. So this equation is same as what we got while calculating the capacitance of coaxial cylindrical capacitor. So in this way also we can find it. So similar way you can try to obtain for the case of parallel plate capacitor. I have made the derivation for the parallel plate capacitor in the material. You can please go through them. If you still don't understand or have some queries, you can leave your comments in the comment section below. I will answer to your queries from there. Thank you. Thank you very much.